Hello and welcome everyone. So let's have a look at this here. We're going to start off with something like this here. We're going to look at an isosceles triangle ABD. We're going to draw an additional triangle BCD so that the triangles share base BD and these are congruent. Okay, so I guess the first thing we should do again is just look at this one step at a time. Okay, got an isosceles triangle. We're told we have a base BD here, so we know that means the other two sides are going to be congruent here. So that means our picture is going to look something like this. Now, it really doesn't matter here how you set this up here, as long as it follows the information that's there. Our bases look like this here. Here's A, okay? We're going to draw an additional triangle. They share base BD, and CDB should be congruent to ABD here. Okay, so the biggest clue here is to note that we have this sort of congruence here. So C should correspond with A, D with B, and B with D here. So it's going to go in the opposite direction like this. So the only way we can really do something like that is by putting this in here. Okay. Alrighty. So now our quadrilateral looks something like this here, and I think we can kind of see what's going on. These two triangles are congruent. So the first thing to note here is that this is an isosceles triangle, right? So that means these two things here are congruent, like so, right? So AB and AD are congruent here. And we also note that in this situation, because these two triangles here are congruent to one another, this means AB corresponds to CD, so these are congruent here, and AD corresponds to BC, so these are congruent here. So now that we have this looks pretty straightforward here, I think. I think now we can kind of see here that there's a thing going on here. It's pretty clear that this quadrilateral here has four congruent sides, right? So we know here, we can go ahead and mark this down. We got four congruent sides, right? Another thing to note about this quadrilateral here, ladies and gentlemen, is that, yes, these are four congruent sides here. Now let's have a look at the angles, right? We can kind of see this is the case here, this angle here. These two angles are green. They should match up here. Similarly, you know, because of the way that the correspondence works here, corresponding parts of congruent triangles are congruent, so it gets us these as well. So in fact, all these angles are congruent to one another, so that's going to be really helpful to us here. Furthermore, we also have the vertex angles A and C. These two are also congruent as well. So we actually have a lot of ways to show that this is this quadrilateral here. We note that this is four congruent sides, so it makes sense here that this is a parallelogram, right? Now there are a lot of pieces of evidence for this here. We have, you know, two pairs of opposite congruent sides, we got two pairs of opposite congruent angles, and what have you here. So really, there's not much we can, you know, that kind of detracts from this here. But we end up with something that looks like this, and that we have this here, this parallelogram here. Note that has four congruent sides. So for something like this here, this is going to be another sort of our special types of quadrilaterals here. We're going to define this quadrilateral here. This quadrilateral, I'm going to define this as a rhombus here. So this here, ABCD, is going to be our archetypical example, what we refer to as the rhombus. So we define it like this here. Quadrilateral is a rhombus if and only if it is a parallelogram with congruent consecutive sides here, okay? And again, note that this definition here is relatively complete, even if it's a little sparse. And we're going to talk a little bit about this a little bit more in the in-class session here, so keep that in mind. Now, let's go back to here. Now, in this situation here, right, when we look at these quadrilaterals here, we notice that there are a bunch of these sorts of things here that must be true. So, for instance, something like this here, in this case, ABCD here, we kind of have ourselves as a parallelogram. So all the properties of the parallelogram should hold for this rhombus here. The opposite sides are parallel, the opposite sides are congruent, and so on and so forth. Now, we note that there's also something involving the diagonal, so I'm going to go ahead and sketch that in here. Let's go ahead and draw in this last bit here. Now, owing to the fact that this is a parallelogram here, ladies and gentlemen, we know that E is the midpoint of both pieces here. So BE and ED are congruent, AE and EC are congruent here, so I can mark that. Oops. Now, something you may have noticed here is that you have a bunch of congruent triangles here, right? It shouldn't be too hard to show AEB and AED congruent here. And same thing with CEB and CED here. So notice that we have a bunch of congruent triangles. In fact, these two are congruent here, these two are congruent here. And it shouldn't be too hard to show that the opposite pairs are congruent as well. So we kind of have four congruent triangles. And in fact, it looks like they're all congruent to one another here, which means that all the angles, AEB, AED, BEC, and ECD here, are all happen to be congruent to one another. Now, wait a minute, these are all around a single point E, so that means here, all those angles, since, you know, those angles sum to 360, we got four of them here, so that means each of those angles has to be 360 over 4, or 90 degrees, which implies something very important here. This means that all these angles here are right angles, which is a big important thing for the rhombus here, that all of these angles are right angles here, which implies that the diagonals are perpendicular to one another. And that's another very big redeeming quality of the rhombus here. Alternately, you could have noticed, wait a minute, there's an easier way to see this here. We note that at this point A, B, and AD here are congruent. That means A is the same distance away from B and D, so it's equidistant from B and D. Similarly, C is equidistant from B and D here. You may recall one of our equidistance theorems that points that are equidistant from from the endpoints of a line segment must be on a perpendicular bisector of that line segment. So A and C are on a perpendicular bisector. But wait a minute, a line segment can only have 2 points of term in any line segment here, so that means if both A and C are on the perpendicular bisector, they must create the perpendicular bisector here, right? And also note, by the way, ladies and gentlemen, we can actually continue with this here. We got a pair of green angles here, a pair of green angles here, and the red angles are also congruent as well, right? Even though the two red angles are congruent, we also have something else going on here, right? In this case, BAE and DAE here, we've showed that those two triangles are congruent. So that means these two angles up here, these two ones with the two black dots here are congruent here. Same thing down here with BCE and DCE here. The same is true like that as well. So we kind of have that sort of thing going on here. So we can actually show that this is true for everything here. So for our rhombus, we actually have several properties here that we're going to focus on. Okay. Now note that the unique properties of the rhombus here focus on the rhombus's diagonals here. And that's going to be something that's going to be relatively true. If you think about what happened, one of the unique properties of the rectangle focused on the diagonals of the rectangle. And we're going to continue with that here. So the properties of the rhombus here, right, has all the properties of the parallelogram. And note that makes sense because it has, if you look back, our definition had parallelogram in it. So we have this here. All the sides of the rhombus are congruent here. The diagonals will bisect the rhombus's angle. That's something I did show here, right? We can show that the pair of green angles and the two black angles up there. And also the diagonals are perpendicular. So keep these last two in mind because these are going to be really important for rhombuses. Now, to show that something here is a rhombus here, right, we can kind of go backwards, right? We can actually show that something has to be a rhombus by simply following the definition here. We can see that as long as you can show the definition here, you're guaranteed a rhombus. Alternately, you could also do something else here. Note that if you want to show a quadrilateral as a rhombus here, and I'm actually not going to prove this right now, I'm going to have you actually focus on this in the homework. We're going to be looking at one of the examples here. You first have to show it's a parallelogram, because as you think about it, our definition contains a parallelogram. And then you can show any one of the following here. So this first part is the definition here. So this just, does it follow the definition? If it does, it's a rhombus for sure. You can also show that if the diagonals are perpendicular, it must be a rhombus here. That is actually going to be I think that's one of the homework problems that you're going to be looking at. Or you can show that a diagonal bisects opposite angles. That would actually guarantee that it's a rhombus as well. So you can use any of these three criteria to show that this is a rhombus here. And we're going to look at that a little bit more as we go. Okay.